I will be your tutor for this subject, Digital System 1. And then we'll be doing some screenshot video and as well some live video when I will be working with the whiteboard. So since it's just an introduction video and we'll be focused on Unit 1, which is based on Chapter 1. And then on our subject today, we're gonna do to the tutor. My name is Joey Monday. Will be your tutor for this subject, Digital System 1. And then today we'll be focused on Unit 1. So we'll try to mix a bit of the two kind of video, which is a screenshot or a video when I'll be working using a whiteboard. So on today's video, it's just an introduction to the subject, but already we're gonna make sure that we finish Chapter 1. And then Chapter 2, we can split it into different video so that you can be able to master each point. And we just gonna talk about a bit of a digital and analog quantity. We are not gonna go deep in the subject. We're just gonna give you some important points like the definition of a digital quantity or analog system. And then we're gonna talk about the binary digit, logic level, and as well the digital waveform. Not deep in the subject, but there will be a textbook that you can download from our website, and then you can go deep into it. But if there is a question, you can always try to ask it in the group where I will be your administrator. And therefore, we also gonna talk about the basic logic function, okay? And then, as I said, we start with our first point today. It's digital and analog quantity. Electronic circuit can be divided into two broad categories, and the first one is our analog. And analogs, when you define it, involve quantity with continuous value. Like for instance, when you look at temperature, time, distance, and sound, those are our analog quantity because they are continuous. Okay, and then we're gonna have a look on this graph to see how do we mean that this is a continuous function. So for instance, when I take, you can see that when you have a sound is a continuous quantity because it doesn't have a hand. Like a road, distance, everything, the time is also a continuous quantity. So those will be our analog category of the board that we said. Okay, and then as we said, we also have a digital category of circuit. So this involves quantity with discrete value. Like when you look at your phone, your laptop, your TV, those are information have been processed, but you are not able to see it. You just see the output. So the quantity are discrete. Okay. So when they ask you a definition on what is the analog or a digital quantity, this is the definition that you should give. So also what you should know is to know what is the advantage of a digital system, because we all have digital equipment. You have your phone, you have your laptop. Those are digital systems. So what are the advantages of those digital systems? It can be processed and transferred more efficiently than analog system. Like for instance, when you use your phone to transfer your WhatsApp message or your picture, it's a digital system. It's easily transferred. You can receive it anytime and anyway, you see. And then another advantage is noise doesn't affect digital system but affects analog system. The analog system, it can be affected by noise. Okay. And then therefore another one, we can say digital system data has a greater advantage of storage. You easily store your movie, you easily store your music, you easily store all your information. So that's the advantage of the digital system. And lastly, we say the digital system has a great advantage of storage. You easily store your information in a flash USB, you can store it on your laptop, you can store it in a CD, you can store it on all those because they are digital content. It's really easy for them to store. You get a point. But we're gonna have a look on an example because there is some way for us to change digital system to analog system. Those are conversion, and then you can move from an analog system to a digital system. Like for instance, like now, what I'm doing, I'm recording a analog quantity, which is my voice, a sound, to a digital system so that it can be recorded, it can be set on this video that you are watching now. And then the second part of our lesson today, it's all about binary digits, logic level, and as well the digital waveform. Okay, so when it comes to binary digit, the digital electronic involve circuit and system in which there are only two states. Okay, so when it comes to digital system, we only want to have a system where we only have two states, and the two states is high and low, 1 and 0. So we'll be dealing with these two states all the way around. Like the information, like my voice now, it records. It's a voice that I'm speaking, but on my laptop, what is set is these two states, 0, 1, 0, 1, 0, 1 is the one that is recorded in order to give you that sound. So a combination to this number is what made my voice to be recorded in a digital system. The two states number system is called binary. So it is a definition that you should know. Binary digits, so we have a binary digit 0 and 1. It's called bit when we have a contraction of this binary digit. A combination to 0, 1, 0, 1, it's become our bit. Okay? And therefore, let's have a look on our logic level. Logic level, basically what we're talking about here is the voltage used to represent a 1, or a 0. Okay? Like for instance, when I look at this wave, first wave, if I start from 0 here, okay, so this represents a 1, higher state, 1 or on, okay. But if I come here and this is start from 0, this represents a 0 because this will become our base, and then this is our base, okay. So we can use a logic level to represent a 1 and a 0. When it's up, we say it's high state, 1 or on. But when it's going down, we say it's a lower state. Okay? So you should be used to this notation because when we're talking about waveform, we'll be playing around with this wave. When you have a higher form, like which means it's going like this up, it's become a 1. It represents 1. But when it's going down like this, it represents a 0. And then digital waveform consists of a voltage level that are changing back and forth between high and low level. Okay, so I will use your textbook just as a reference to explain you what happened with this digital waveform. Okay, we have two types. We have a positive going pulse and as well a negative pulse. When it comes to a positive going pulse, we have the rising, it's happening on from 0 to from low to high, okay. But the falling, it's moving from higher to low. But with a negative going pulse, it's just the inverse. We are moving from a higher to low. This it become falling edge, and then rising edge, it's from lower to high. These are just the type of pulse that you can have: a positive going pulse or a negative going pulse. Okay, the two they are just inverse to each other. And therefore, as we explained there, those waves that we explained were ideal waveform. Now we have a non-ideal waveform, because when I'm recording my voice, it's not a ideal waveform that it records. It's a non-ideal waveform, but some calculation need to be done in order for this wave to be a ideal form. Okay, so you have the rising and as well the falling, and this wave is not an ideal waveform, it's always a non-ideal form. But we have a linear amplifier which move a non-linear to a ideal waveform. Another point we can discuss under the waveform characteristic is, as we said, we have this ideal form, okay, a square wave. We have the one that's periodic. Periodic, it means we have a repetition of a same wave after time to time. Like you can see, you have a first period, and the first period is the same to the second period, and is the same to the third period, okay? But this second one is a non-ideal or a non-periodic waveform because there is no any repetition here, okay? So you know the frequency is given as 1 over the period so you know that your frequency is given by 1 over the period, and your period is going to be the inverse of that, okay? And then from this example, which is a ideal waveform, as we discussed, we have our pulse width, okay? So the period to this wave, you can see the repetition start again here. So this is gonna be our period from that point to this point, okay? And then the pulse width is gonna be only this part. Those are our pulse width, okay? And therefore, if we have been asked to calculate the period, we know that the period is can be from 0 to 10. So this will be our period, 10 milliseconds. And when it comes to the frequency, you know it's going to be 1 over the period. And then our duty cycle from the formula is given by the pulse width over the period. The pulse width is how much? You can see that it's only 1. Even here, if you take 11 from minus 1, you have 1. So you can calculate the duty cycle of this ideal waveform. And therefore, from our digital waveform that we had a look, we realized that we have a pulse amplitude, which is the higher from the baseline, okay? And then you have your rise time. The rise time is the time required for a pulse to go from its low level to its higher level. Measure from 10% to 90% of the pulse amplitude. A full time, if they ask you the definition, this is the system should give the time required for a pulse to go from its higher level to the low level, and it measures the 90% to 10% pulse of the pulse amplitude. So when we talk about this measurement, is when our waveform is not ideal, a no ideal waveform. A pulse wave, this is the measure of the direction of the pulse. How long does our wave pulse take from higher level to the low level? So that gap is what we call our pulse width. On this example, and then we're gonna see how to work with a non-ideal waveform. And then when it comes to the non-ideal waveform, we'll be looking for our rise time, our fall time, and as well our pulse width. Okay, so you come here, as we said, when it comes to the rise time, we need to check at 10% from 10 to 90%. But let's determine first of all what will be our amplitude, and then for the fall you have 90 to 10 the falling amplitude, and then here it's just 50% of our amplitude. So in order for you to get your amplitude, you check your waveform, and then you can see it's 10. So we can say our amplitude of this waveform is 10 volt. Okay, so when it comes, so after we have identified our rising time, we need to check for 10% of our amplitude. Our amplitude is 10 volt. What is the 10% of 10 volt? It's 1. So this will be our 10%. Okay, and it's simple to do the calculation. Just to take 10 times 0.1 or times 10% of the amplitude. So it's gonna give you 1. Again, you look for your 90% of 10. 10 times 90%. This will give us 9. So once you come here, you take this to be your 90%. So let's check. Look now, you have a 90 and a 10%. And then this, okay? And then you project it down to the timing. Can you see that? Okay? So therefore, this part here will be our rising time. Okay? So how do we do the calculation? This is 1, so you can say it's 0.9. It's going to be 0.9, and then here you have 0.2 minus 0.2, and therefore our rising time is going to be 0.7 microsecond. Okay? And then you do the same for the falling time. Now look at how the graph is. So you move with it until to the falling, and then you move with the 10% until the falling. So you go with it down, you go with it down, and therefore your falling time is gonna be this time here. Okay, so therefore when you calculate your falling time, it's going to be what? As you can see here, it's 5. So this can be, maybe let's say for instance 5.3 minus, and then you check here, this is gonna be 4.6. Okay, so when you take 5.3 minus 4.6, you can see that this is going to give us as well 7 microseconds as your falling time. Okay, but when it comes to the pulse wave, okay, first of all we have to check what is 50% of our amplitude, and then you can see it's 5. So we go to the graph, you check, this is a 50% of our Nonideal with okay, and then now we have there 50-50. So you drop your 50, and then you drop the 50 down there. Okay, and therefore our pulse wave will be this vector TW. Okay, so how do you calculate it? You come, you say my pulse wave. Okay, if I check here the last part, you can see it take 4.3. Then you look here, you can check 50, it's 0.5, then minus 0.5. So this is going to give us 3 point how do you say 3.8 microseconds. So that's how you do this small calculation when it comes to this graph, a Nonideal graph. Okay, as we explained from our video on the whiteboard, we say when it comes to the rise time, it's measured between the 10%, okay, and the 90% of our amplitude. So you go with it, it drop there, and then that. So this will be your rise time. But when it comes to the fall time, you go with it. It's gonna be between that, and then you go with it, and then that. This will be your fall time. Okay, and then when it comes to our pulse width, this will be your pulse width, as I explained it on the whiteboard so that you can understand what happened. So this small calculation, you should be able to do them yourself when it's asked on a test or an assignment. And therefore, we're gonna move on our last part of this video on our lesson. It's a basic logic function. So we have three basic logic functions. The first one is a not function. Not function. So it's called an inverter. Why is it called an inverter? Because already from its symbol, this means we are doing inversion. Okay? So for instance, if I come with 0, which is a low state, I'm going to invert it to what? To a 1, to a higher state. If my input is 0, my output will change to 1. I'm just doing inversion. And then if my input is 1, my output will be 0. Okay? For instance, if I apply a 1 here, my output will be 0. And by definition, our not function operation change one logic level to a opposite level of the one that you put in. Okay. Another function, because we say we have three, is a AND function. How do we deal with the AND function? Which is the AND function? The symbol is this, and the operation of this function is multiplication. Okay, so from definition, if it asks what is an AND function, an operation produces a high voltage only when all the inputs are high. Okay, so for instance, if I come here with a 0 on A and 0 on B, I'm doing multiplication. 0 times 0, how much we get? 0 times 0, I have 0. So if I come again with a 0 to here and then 1 there, 0 times 1, I have what? 0. So if I come again with a 1 and 0, 1 times 0, how much do I have? 0. But if I come with 1 times 1, I have 1. So the operation for a AND function, which is the AND gate, it's multiplication. It's only when I have 1, 1, 1, 1 is when my input is going to be what? My output is going to be 1. And then the last function is a OR function. Okay? And a OR function, the symbol of a OR function, this is the symbol. Okay? But the operation that is doing addition. Okay? So that's why by definition we say a operation produces a high output only when one or more inputs are high. So we are doing addition. If I come here, I say 0 plus 0, it gives us what? 0. If I say 0 plus 1, I'm going to have what? 1. So it's basically like you are coming with an input information. You put here 0 plus 0. It gives you 0 on C. If you come with 0 plus 1, you have what? 1. If you come with 1 and 0 at B, you get what? 1. If you have 1 plus 1, you have 1. So with this gate, we are doing addition, but the output is going to be high. Only one or more inputs are high. It's addition. Okay? So this is our lesson for this unit. It's basically your chapter 1. So if there is any question, you can always try to ask them in private or in the group so that I will assist you personally.